Alright, so today we are covering, still don't know how to say his name, Ado's theorem? And quick note they have at the front, I'll repeat, we're doing all this with finite dimensional algebras over a field of characteristic 0. So we start out with coefficients of a representation. So we're going to let U be an associative algebra with unit. It's going to be over our field K. With a vector dual as a vector space the typical U star and rho a representation of U on a vector space E. Then for E in our vector space being acted on and E prime in its dual, let theta of E and E prime be the corresponding coefficient of rho as theta of E prime acting on X is going to be equal to the inner product of rho as a representation of X acting on E with E prime. Noting that the mapping from E to this theta E prime for fixed E prime is a homomorphism of E as a U module into U star of the co-regular representation of U therefore the vector subspace of U star generated by the coefficients of rho, which we will be calling C of rho, is a U submodule of our U star. If we have EI prime generating E star over K the mapping from E into the set of theta E with each EI prime is injective homomorphism, U homomorphism that is, of E. Okay, and these EI are indexed by an indexing set I. It says injective homomorphism of E into I copies of C of rho as if you have theta of E and EI prime equals 0 for all I, implies that the inner product of EI prime is equal to the inner product of course, rho of 1E of EI prime, which is equal to the coefficient of E and EI prime on 1, which is 0 for all I, so E is 0. We note that if U is the enveloping algebra of a Lie algebra G with representation rho on a n-dimensional vector space E, E as a G module is isomorphic to a G submodule of C of rho to the n. Alright. And now we have the extension theorem, which is something, I'm sure. So let G be a Lie algebra which is the sum of an ideal G prime and a subalgebra H. Let U the enveloping algebra of G and U prime and U the enveloping algebra of our G prime. There exists a unique G module structure on U prime such that they have two conditions here, which they labeled alpha, as for x in G, U in U prime, the u action of x on u is equal to negative ux. And we also have condition beta, which has for x in h and u in u prime, the action of this x, the action of x and h on u is xu minus ux, which is an inner derivation of u defined by x, and so it leaves g prime and so u prime stable. These define a unique linear map x into this u should be u prime, and so should this one actually, into x u prime of g into the k-linear maps of the universal algebra of the ideal. We only need to show that the bracket of x and y in u prime the result of that acting on u prime is x acting on u prime, comma, y on u prime. Now, given that x and y can come from either h or g prime, there's three cases to consider, since the order in which they come from doesn't matter. So if they're both from the ideal, then x comma y acting on u prime on some u is equal to just negative u of xy minus yx, which is x u prime y u prime minus y u prime x u prime acting on u. In the set in case 2, we have x and h and y and g prime. This also covers x and g prime and y and h. Bracket of x and y and u prime acting on u is once again negative u of x y minus yx, which is equal to x of minus negative u y minus negative u y of x plus x u minus u x of y is equal to x acting on u prime, y prime, and it's just we get back our bracket again. And in case 3, we have x in h and y in h. In this case, we don't have a formulaic proof. We have that x and y on u prime and x u prime, y u prime are both derivations of u prime whose restriction to g prime coincide with their G adjoint of X and Y, and this, and add G adjoint of X, bracket G adjoint of Y, hence, and so they are equal. We will also consider the dual representation of X to the negative transpose of the action of X on U of G on the dual space of the universal developing algebra of G prime. So for X in G, this negative X U transpose is the transpose of right multiplication by X in U prime the corresponding representation of U prime is therefore the coregular representation of U prime. Alright. Sorry. Alright, so we now have a definition. Let G be a Lie algebra with subalgebra G prime, and we have rho prime representation of G prime on V prime. Now, a representation rho of G on V is an extension, it's called an extension of rho prime to G if there exists an injective homomorphism of it as a G module, G prime module into the G prime module V. This is of course going to be V prime, I didn't write that out. We say that the G module V is an extension of the G prime module V prime. Now, if rho prime is finite dimensional and G prime is a solvable ideal of G, for a finite dimensional extension to exist, we must have the bracket of G and this G prime is contained in the largest nilpotent ideal of our rho prime. And this comes with a theorem which is by Zassenhaus, I guess. Another name I don't know how to pronounce. All of those in math, I have one, so hopefully it should help me in math. So we're going to let G equals G prime plus H be a Lie algebra as the direct sum of an ideal G prime and a subalgebra H and rho prime, a finite dimensional representation of G prime whose largest nilpotency ideal contains this bracket of H and G prime. Then condition A, there exists a finite dimensional extension rho of this rho prime whose largest nilpotency ideal contains that of rho prime. Condition B, if for all x in H the restriction of the G adjoint of x to G prime is nilpotent, rho can be chosen such that the largest nilpotency ideal of rho contains H. Let's look at the proof. Okay. Let U prime be the enveloping algebra of G prime with U prime and U prime star having the previously defined G module structures. Right, so we're going to let I and U prime be the kernel of rho prime which makes it a two-sided ideal of U prime of finite codimension. A subspace of C of rho prime of U prime star is orthogonal to I. Let S be the G submodule of U prime star generated by C of rho prime. And we have here that C of rho prime is inside of S, which is inside of U prime star. Now we have that S is finite dimensional over K. Well, how do we know this? I'm going to let V prime be the space on which our rho prime operates. And V prime be V prime 0 inside V prime 1 inside all the way up to V prime D, which is going to be 0. It would be a Jordan hurdle. I've been calling it holder. It's probably hurdler series. That's probably, I mean, that's clearly not right either, but I'm thinking it's closer. Of the G prime module V prime, let rho prime I be the representation of G prime on V prime of I minus 1 over V prime of I derived from rho prime. And we're going to let I prime and U prime be the intersection of the kernels of each rho I prime. So I prime D is in I, which is in I prime, and the intersection of this I prime and G prime is the largest nilpotency ideal of rho prime. By a previous corollary, we have that I prime D is finite of finite codimension in U prime. If X is an H, the derivation sending U to XU minus UX, this derivation of U prime maps G prime into the bracket of G prime and H inside of I prime, hence U prime into I prime and I prime D into itself. Now, as I prime D is a G prime submodule of U prime, it is a G submodule of U. The orthogonal of this I prime D in U star is finite dimensional as a G submodule which contains C of rho prime and so contains S. Thus S is finite dimensional over K. And this is from, okay, and then, so then for X in the intersection of this I prime and G prime, XD is contained in the annihilator of the G module U prime over I prime D, and hence is in the annihilator of the G module S. 1 second. Alright. So I believe that is part of it. We have its finite dimensional on that, so we have a bit more to go. So we saw that the G prime module V prime is isomorphic to a G prime submodule of the product C of rho prime to the n. Hence, the G module S to the n provides a finite dimensional extension rho of our rho prime to G. Also, we have that rho x is nilpotent for x in I prime intersection G prime, as the intersection of I prime and G prime is an ideal of G containing the bracket of H and G prime. We get that I prime intersection G prime is contained in the largest nilpotency ideal of rho, which gives us A. Now we're going to finally suppose for all x in H, the restriction of the adjoint in G of x to G prime is nilpotent. As the elements of H operate on U prime by derivations, for all U in U prime and x in H, there exists an integer E such that x to the U prime to the power of E acting on U is 0. So it tells us the endomorphisms derived from x U prime on each U prime over I prime D and on S are therefore obviously going to be nilpotent. Thus, rho of x is nilpotent for all x in H. As we have seen proof of this already for x in the intersection of I prime and G prime. So the intersection of I prime and G prime is an ideal of G prime containing the bracket of H and G prime, and the sum of H and the intersection of I prime with G prime is an ideal. We finish through a lemma. And so we get a lemma now let G be G prime plus H, a Lie algebra as the sum of an ideal G prime and a subalgebra H. Let sigma be a finite dimensional representation of G. Now suppose that sigma of x is nilpotent for all x in G prime and for all x in H. Then sigma x is nilpotent for all x in G. The proof. By quotient of kernel sigma, we can assume sigma is faithful. Then G prime and H are nilpotent. And hence, G being an extension of a quotient of H by G is solvable. Then H and G prime are contained in the largest nilpotent ideal nilpotency ideal of sigma. Alright, now I think we only have one more section in this whole book, I believe, and it's a pretty short one, so we're gonna go a bit over time here, and we're just gonna finish here, and that I mean, this is what we're covering here is Ato's theorem, which, I mean, was the point of all this anyways, right? So, it starts out with a proposition. Let G be not nilpotent. G is a Lie algebra. N is its largest nilpotent ideal. A and G a nilpotent ideal. And rho a finite dimensional representation of A. Such that every element of rho A is nilpotent. Then sigma admits rho, I don't know why I always call it sigma, rho admits a finite dimensional extension sigma to G such that every element of sigma of n is nilpotent. And the proof, let A be equal to n0 inside n1 up until np, which is n, be a sequence of subalgebras of n such that n of I minus 1 is an ideal of ni of codimension 1. Then ni is the direct sum of ni minus 1 and a one-dimensional subalgebra. As the n adjoint of x is nilpotent for all x in n. I specify all x in my context. You can find finite dimensional extensions of row 1 up and through row p is row prime of row. These all extend row to n1 up and through np equals n, such that every element of row prime of n is nilpotent. Now we've got a little more work to do on this proposition here. My hand is just very tired right now, and I'm just trying to soften it up a little bit here. going to let R be the radical of G, and n equals R0 inside R1 all the way up to RQ is R a sequence of subalgebras of R such that R to the I minus 1 is an ideal of Ri of codimension 1. Thus, Ri is as above is the sum of Ri minus 1 and a one-dimensional subalgebra. As the derived algebra of R is inside of N, we can find, once again, finite dimensional extensions. Rho 1 prime up to rho q prime, which we're going to set equal to rho double prime of our rho prime to R1 up through RQ equals R, such that every element of rho double prime of N is nilpotent. Now, as G is the direct sum of R and a subalgebra S, and that the bracket of S and R is inside of N, we can find a finite dimensional extension sigma of R double prime to G, rho double prime to G, such that every element of sigma of N is nilpotent. Now we have a theorem which they state twice. Kind of. Theorem. Every Lie algebra has a finite dimensional faithful linear representation, which we can alternatively state as Ato's theorem. I guess better state as Ato's let G be a Lie algebra with largest nilpotent ideal N. There exists a finite dimensional faithful representation row of G such that every element of row of the largest nilpotent ideal is itself nilpotent. And let's look at the proof. The one-dimensional Lie algebra K admits a finite dimensional faithful representations TAF such that every element of TAF K is nilpotent, such as the map sending lambda to the left shift of lambda multiplied left shift multiplied by you see the matrix. The two-dimensional left shift multiplied by lambda. Thus the center C of G as the product of one-dimensional algebras admits a finite dimensional faithful representation sigma such that every element of sigma of C is nilpotent. Let sigma 1 be a finite dimensional extension of sigma to G such that every element of sigma 1n is nilpotent, as we saw above, if k is equal to the kernel of sigma 1, then the intersection of k with the center has to be 0. Now we're going to let sigma 2 be the adjoint representation of G, which is going to have a kernel being C, of course, and every element of sigma 2 and being nilpotent. The direct sum, which we're calling rho, of sigma 1 and sigma 2 is then finite dimensional. Every element of rho n is nilpotent, and the kernel of rho is 0 as it has to be contained in both K and C, so that rho is faithful. And we are done with our discussion of nilpotency, I believe. Nilpotency, semi-simplicity, all that fun stuff. That's like the first whole book of Bourbaki, like books one, I don't know how they're divided, but that's the first section of that. So yeah, next up, I think we're actually going to cover Sayre's coverage of representations of the special linear group. And then that's the end of Sayre actually too, and then we're going to go on to Humphrey's discussion of Cartan matrices and associated ideas. So look forward to all that, I guess.